Hello National 5, welcome to week 3 of your remote learning. This week we're going to be having a look at energy. So the plan is to learn about all the different forms of energy, the 4 primary energy equations that you'll need to know, and learn about the conservation of energy. Which means that throughout this week you should learn to name all the different types of energy so you know what's happening. You should be able to recognise when each of those forms of energy is present if you're asked about them in questions. You should be able to identify and use each of the equations, the ones for work done, potential energy, kinetic energy, and the equation that relates energy and power. That last equation you've already met back in the electricity topic. And you would be expected to be able to state the law of energy conservation. So that's the success criteria for this week. So the first thing is that we have our 8 basic forms of energy. We've got heat, light, sound, electrical, potential, kinetic, chemical, and nuclear. Now potential's there with a wee bracket around it saying it's stored energy. That's quite useful because there are different types of potential energy. We've got gravitational potential energy, so for example if I take this ball up, hold it in the air and then drop it, it falls down. It fell because it had stored energy. It had potential energy before it was let go and it fell. Another type of energy this ball also has, which is called elastic energy. So if I squeeze this ball in, when I let go, it returns to its normal shape. That's because when I squeeze it in, I'm storing the elastic potential energy. Now elastic potential isn't one you need to worry about, but gravitational potential energy is. The other one I want to bring up is chemical energy, because chemical energy has a couple of ways it can turn up. Chemical energy is found in things like batteries or cells, but is also food. So you need to remember that that's there too. And you've got this wee reminder at the bottom here that energy cannot be created or destroyed, but it can be changed from one form to another. So we've got a few examples here of energy changes. So for example, dropping a ball. If I hold it up here, it's got potential energy. When I let go of the ball, it falls down and picks up kinetic energies. It speeds up because kinetic energy is a type of movement. It's movement energy. And we will look at kinetic energy more later on. If we turn on a light bulb, well, we're going to get electrical energy, which is powering the light bulb, giving us light and heat. And you need to remember the and heat part. If it's an LED, it's just light. LEDs are really efficient. They do not lose any significant amount of energy to heat. When we're using a speaker, what ends up happening is the electrical energy surges through, and there's almost like a curved plate at the back which is caused to vibrate, which gives us kinetic energy. That's why if you're sitting in a car and the speakers are going really loudly, you can feel it vibrate, and that's coming from the speakers, and that kinetic energy then makes the sound energy. Finally, if you've got rubbing hands together, you're turning the kinetic energy of them moving into heat and sound. And frankly, any type of frictional event is going to have that energy change. That the kinetic energy of the moving object gets turned into heat and sound. So, we need to introduce our first equation. This is called work done. Work done is the energy required to move an object a horizontal distance. And we just calculate it by taking the force and multiplying it by the distance. I've included the formula triangle at the bottom left. Please remember, if you're planning on doing higher physics next year, you need to get out of the habit of using formula triangles. So I'm including these for people who are struggling, and do make use of them if you are struggling. But similarly, if you're struggling with these equations, higher physics is going to be a real struggle. Work done, measured in joules, because it's a type of energy, force measured in newtons, distance measured in meters. So we're going to have a look at an example here. So a person exerts a force of 120 newtons in a barrel and pushes it a distance of 50 metres. Calculate the work done by the person. Well, all we need to do is write out our equation, E equals Fd. We don't need to rearrange it, so we just substitute in the numbers. E equals 120 times 50 gives us 6,000 joules. And honestly, that's about it when it comes to E equals Fd. There's nuances in where we can ask the question, sure, but it's not particularly hard to understand. What we do need to do is we also need to think about what happens if we lift an object, because this is about pushing or rolling an object on a flat surface. So what happens if we lift it in the air? Well, instead of using the force required to lift an object is just its weight. So we sub out the force for weight. So instead of having F, we've got W, and we know that W equals mg. That's an equation we've already covered. And the height we're lifting it, well, we can just call that h, because it doesn't need to be distance, it's just the height. And when we swap around these, we end up getting a different equation for gravitational potential energy, where we now have gravitational potential energy, and because it's energy, it's measured in joules, is equal to mass, measured in kilograms, times g, gravitational field strength in newtons per kilogram, times h, height, measured in meters. So remember, gravitational field strength, if you do not know the gravitational field strength, or it's not told to you, you can assume it's Earth. And if you're told it's somewhere else, another planet, and you don't know the gravitational field strength for it, or the gravitational field strength for Earth, you can go and have a look in the data book. The data book will tell you the gravitational field strength for any relevant planetary objects. Once again, I've got a formula triangle down here. It's looking a wee bit worse this time because there's 4 factors included in it. But again, still there to be used if you need it. So let's have a look at some examples. A crane exerts a steady force of 5,000 newtons while slowly lifting a large crate to a height of 4 meters. How much work is done by the crane? Well, we're being told a force, and we're being told the distance it's travelled. Doesn't matter that it's height, we're still being told a force and a distance. So it's E equals Fd, and that gives us 20,000 joules. Now we're being asked how much gravitational potential energy is gained by the crate. Well, we did 20,000 joules worth of work to lift it up. That energy hasn't gone anywhere, it's just been changed from one form to another. It has gone from being work done to being gravitational potential energy. So once it's up there, it has gained 20,000 joules. A crate of mass 4 kilograms is lifted 3 meters. How much gravitational potential energy is gained by the crate? This time we do use E equals mgh. We substitute in the numbers to give us 4 times 9.8 times 3, which gives us 118 joules gained by the crate. We do have the more complex one to deal with now, which is kinetic energy. So if we've got something, we push it along a bench, it gains kinetic energy, and again, it's going to be equal to the work done, but when we need to try and figure out what the kinetic energy is in terms of a calculation, we need to know the mass and the speed of the object. And the kinetic energy of the object is given by E equals a half mv squared. Again, I've given a formula triangle. This one, frankly, it's probably not as much help as you might think. because you need to remember to manipulate any of the terms. But I included it for completeness' sake. Because kinetic energy is again a form of energy, it's measured in joules, mass is measured in kilograms, and speed is measured in meters per second. Please, please, please remember, if you have to do a calculation and you're finding v, you need to find the square root. You need to take the square root of everything at the end. You can't give an answer in v squared and get the marks. It's got to be v. It's got to be speed. And again, if you're putting numbers into the equation, if you forget to write down the squared in the line where you substitute in the numbers, you're not going to get marks for that line or any line following it. So you need to be very careful about remembering to include that squared at each stage. So let's look at some examples here. A cricket ball with mass of 0.8 kilograms is thrown with a speed of 20 meters per second. Calculate the kinetic energy of the ball. So we write the equation, E equals a half mv squared. We substitute in the numbers and we get out kinetic energy of 160 joules. For part B, we're asked, how fast would the ball have to travel for its kinetic energy to double? The first part of that is we need to write in the equation, E equals a half mv squared. We want to know how fast it would travel for its kinetic energy to double. That means that we're trying to find what this is when the kinetic energy is double 160 joules. So the energy would be 320 joules equals a half the mass times the same, 0.8 times v squared. Now we rearrange for v. So v equals the square root of 320 over 0.4, and that means that in order for the kinetic energy to double, it's got to be travelling at 28.3 meters per second. So only 8.3 meters per second faster, and the kinetic energy doubled. And that definitely isn't what I would have predicted immediately. I'm just going to remind you about the conservation of energy part of this. So energy cannot be created nor destroyed, but it can be changed from one form into another. That is the law of conservation of energy, or the law of energy conservation. So if a falling object loses a certain amount of gravitational potential energy and it gains the same amount, so for example, if a falling object loses a certain amount of gravitational potential energy, it will gain the same amount of kinetic energy, assuming there's no friction or no other form of energy is produced. Here's a question which is designed to have a look at conservation of energy. A stone of mass 4 kilograms is dropped from a height of 5 meters. Calculate its speed when it hits the ground. We need to think about what this question wants. This question wants to know the speed of a stone when it hits the ground. We've been given the mass of the object, but the equation for kinetic energy is E equals a half mv squared. We don't have energy. But we do have enough information to find energy. We have been told the mass of the stone and the height it was at. So we've got M and H. We've not been told G, the gravitational field strength, but we can presume we're on Earth. So we have the information to find the potential energy. So if we do that, if we do E equals mgh, substitute in our numbers, and we calculate its potential energy as being 196 joules, we can then use the equation for kinetic energy, which is E equals a half mv squared. We can put in the 196 joules from the potential energy, the 4 kilograms from the mass, and then show that V, the speed when it hits the ground, is equal to 9.9 meters per second. We're then told if the same stone is thrown upwards at 9.9 meters per second, what height could it reach? Well, we could do E equals a half mv squared, find the kinetic energy, and then substitute that into E equals mgh and find out the height. But we don't have to, because the calculation we just did before this was for the same stone, and the speed that it hit the ground at was 9.9 meters per second. So when we throw that up at that speed, it will get to the same height. And that means that we know it will reach a height of 5 meters. But question C has challenged me. It's telling me, what assumption have you made about throwing this stone up or when it's falling back down? And I did make one. I've assumed that all the energy is going from potential to kinetic or kinetic to potential energy. And that might not be the case. We're assuming that there's no energies lost due to air resistance or due to friction. That it's not being lost in the form of heat or sound. Okay, those are the 3 equations that you hadn't dealt with before. Here's one that you have. P equals E over T. Power is the energy transferred from one form to another, and power is the work done per unit time. So power is measured in watts, energy in joules, and time is in seconds. An example which might be used in terms of dynamics would be that a person uses 2.3 kilojoules of energy to climb a ladder in 4 seconds, and we're just being asked to calculate the power they used. Well, we've got our P equals E over T. P equals 2,300 divided by 4, and that gives us 575 watts. Another example we could go for is a European swallow uses 1.089 joules of energy every second to fly to its top speed. How much power is it using? Well, it's telling us how much energy is being used each second, so P equals E over T equals 1.089 over 1 equals 1.09 watts. Remember, 3 significant figures is the right number to be dealing with. If it has the mass of 18 grams, what is the speed of the unladen swallow? So we've got our energy, which we've said is 1.089 joules. We've got a mass of 18 grams, so we substitute that in. Remember, mass is normally in kilograms, so you've got to divide by 1,000 to get it in grams. We rearrange it, and we find out that V is equal to 11 meters per second. So that's the speed of an unladen European swallow. Power is an interesting one because power is something that we could assess for humans in class. I mean, we could have checked the power of each person in our class if we wanted to. Because what we could do is we could use set of scales, stand on them, find our mass. We could use a tape measure, measure the height up a set of stairs, and use a timer to time us as we ran up the stairs. Doing that, we calculate the potential energy that we have gained in a period of time. And then we can use P equals E over T to calculate our power. It's not perfect, but it's a nice fun exercise to do. There are issues with it in that you're not putting all of your energy into potential energy because stairs are at an angle. The timing might not be perfect because you've got hand-eye coordination to deal with, so you'd want to repeat it for reliability. Or, if you could have laser gates, that would be even better. Another big one to think about in terms of energy changes is the energy change used when spacecraft return to Earth. Basically, they slow down by heating up in the atmosphere. There's just a lot of air friction that's entailed. And there are some massive, massive changes in kinetic energy of spacecraft. We can do the calculations individually. We could find out what the kinetic energy is of the spacecraft before it starts to use the atmosphere to slow down, and after it used the atmosphere to slow down, find the difference between them, and we found the change in kinetic energy. That's, in fact, what this equation here is showing. Delta EK, the change in kinetic energy, is equal to half mv squared minus a half mu squared. Basically, v squared is the final speed, minus u squared is the initial speed. What we can do if we want to, though, is we can then figure out how much work was done by friction to slow us down. Because the work done by friction is the change in energy. And however far our spacecraft travelled in that time period, as it slowed from one speed to the other, that's the distance it travelled, and then we could use E equals Fd to find the force of friction being applied over that entire journey. So that decrease in kinetic energy is equal to the work done by friction, and that's the amount of heat that's being produced by it. Honestly, the amount of heat that these space shuttle tiles can handle is absolutely phenomenal. So phenomenal, in fact, I have a wee video to show you on it. So this person just said that that these space shuttle tiles have been in this oven at 2200 degrees for hours. Okay, and that if he put in pizza, it would incinerate. Literally incinerate in minutes. So you can see the amount they're glowing from that massive store of heat that these space shuttle tiles have from being in that oven. So if you think about it, if ever you were to handle these cells, you'd have to be really careful, handle it with these massive metal tongs, or wearing very heavy gloves, etc. Except he's able to pick them up by hand. The space shuttle cells that were used have phenomenal levels of physics associated with it. Now, I can describe what happened in general. Basically, the space shuttle cells were designed so that they absorbed the heat and then emitted it out of specific places. So places that is glowing, if he touched it, his hands would melt. Quite simply, they go. But where it's black, it's not emitting heat. So he can hold it by the edges and not be in danger. Be completely safe. Now, while I can describe what happened in terms of the general idea of the science, there might only be one or two people in the world now who still understand the full science of how they work. I think that's pretty impressive. So we've got our example here of what happens during re-entry. A space shuttle has a mass of 100,000 kilograms and orbits at a speed of 8,000 meters per second. The shuttle enters the atmosphere and air friction slows it down to a landing speed of 100 meters per second. The distance travelled through the atmosphere was 50,000 kilometers. We're to calculate the decrease in kinetic energy and then find the average force of air friction on the shuttle. So, for the first bit, the decrease in kinetic energy, delta EK is equal to a half mv squared minus half mu squared. You could just calculate these as two separate equations and just do a half mv squared and E equals a half mv squared and then take one away from the other. But I'm doing it this way just to show it can be done. So delta EK equals a half of 100,000 times 100 squared minus a half of 100,000 times 8,000 squared. So we find out that the change in kinetic energy is minus 3.2 times 10 to the 12 joules. So an enormous drop in kinetic energy. And then we've got to find what the average force of air friction on the shuttle was. Well, we're going to need to use E equals FD. Remember that the energy here is the 3.2 times 10 to the 12 joules. So that's the force that was being applied. And basically the So then we've got to figure out what was the average force of air friction in the shuttle. Well, that kinetic energy was lost, so it dropped down, and that was changed into the force that was caused by the force of friction. So our energy here, was used to slow it, is 3.2 times 10 to the 12, which is all converted into mostly heat. So that equals F times 5 times 10 to the 7, because it travels that distance through the atmosphere. We rearrange it, and we find out that the force of friction was 64,000 newtons. Now this last bit was quite a hard wee bit to finish on. It can come up as a type of question, but generally it will be broken down into multiple sections for you. That's it for this week. Hopefully that all made sense. So you've got your 3 new equations and a recap of the older one to do with energy and power. We've had a look at the different forms of energy, which is something that's been covered over and over in the school all the way since first year. And a wee bit of a reminder of the consequences of the law of conservation of energy. Have a good week, everyone.